Welcome to today's deep dive. I'm really glad you could join us today because our mission is, well, it's to explore something in physics that sounds honestly like literal magic.
It really does. It sounds completely made up,
Right. But it's actually one of the most striking and frankly useful discoveries of our time. We're talking about superconductors.
which is just a massive topic.
It is, yeah. But to start, I want you to picture yourself in a grocery store parking lot. You grab the handle of your shopping trolley, you line it up, and you give it a really good hard push across the asphalt.
And I mean, we all know exactly how that ends.
Right.
Rattles forward for like a few feet, it slows down, and then it just clunks to a stop.
Exactly. But I want you to imagine a scenario where it doesn't do that. You give that trolley a single push, and instead of scraping to a halt, it just keeps rolling.
Oh, wow. Just forever.
Forever. It rolls out of the parking lot, down the street, across the whole city, and it never, ever slows down. There's just absolutely zero friction. It coasts for eternity on that initial burst of energy.
Which, obviously, in our everyday mechanical world is just completely impossible.
Yeah, friction always wins in the real world.
Always.
So we're looking into a phenomenon today where in the world of electricity, there is actually a way to cheat friction entirely.
Yeah, and it's one of the most astonishing behaviors in all of physics, honestly. Under very specific conditions, certain materials can carry an electric current with zero resistance. Zero. Like you could start a current flowing in a loop of this material, and it would theoretically just flow round and around for millions of years without ever losing even a fraction of its energy.
Which is just wild to think about. And these are called superconductors.
Exactly. Superconductors.
Okay, let's unpack this because if we are going to understand just how monumental a zero resistance material is, we first have to understand the invisible toll that regular resistance takes on our world every single day.
Yeah, the tax we constantly pay.
Right. So I like to picture just ordinary copper wiring, like the stuff running through the walls of your house right now. Electricity is, at its most basic level, just a flow of tiny negatively charged particles, which are electrons, moving through that wire.
And, the mental image most people have is that those electrons are cruising down an empty, open highway.
Like a water pipe or something.
Yeah, exactly, like water in an empty pipe. But the reality at the microscopic level is, well, it's much more chaotic. That copper wire is made of this dense lattice of atoms.
So it's less like an open highway and more like trying to sprint through a really dense, jostling crowd.
That's a perfect way to put it. The wire is essentially an obstacle course. As these tiny electrons try to move forward, they just keep crashing into the copper atoms.
Right. And the problem is compounded, I guess, because those copper atoms aren't even standing perfectly still, are they?
No, not at all. They possess thermal energy, which means they're constantly vibrating in place.
Because they have heat.
Right. And the warmer the wire is, the more aggressively those atoms vibrate, which creates an even more chaotic environment for the electrons trying to pass through.
And every single one of those microscopic crashes has a consequence, right? Like something has to give.
It does. When an electron collides with one of these vibrating atoms, it transfers a little bit of its kinetic energy to that atom.
Okay.
And that actually causes the atom to vibrate even harder. So in our macro world, we experience those intense atomic vibrations as heat.
Oh, interesting.
Yeah, this is the mechanism of electrical resistance. It is literally the electrical equivalent of friction, constantly sapping energy from the current and bleeding it away as heat.
Which totally explains why, like, the glowing metal coils inside a space heater or an old toaster get so intensely hot.
Exactly. That is electrical resistance working by design.
Yeah.
We actually want those billions of electron collisions to generate heat in that case.
Right, I want my toast to get toasted.
Right. But most of the time, we absolutely do not want that heat. I mean, think about the global power grid. When a power station generates electricity, it has to send that current across hundreds of miles of transmission lines just to reach a city.
And because of electrical resistance?
Because of resistance, yeah. A highly meaningful fraction of all the electricity humanity generates is simply lost in transit.
That's incredibly frustrating.
It's massive. It just dissipates into the air as waste heat before it ever even reaches your light switch.
So it really is like an unavoidable universal tax. Resistance is just this tax we pay on every single flow of current everywhere on Earth.
Until we introduce a superconductor.
Okay, here we go.
Because a superconductor doesn't just lower that tax, it abolishes it completely.
And this is where the physics starts to sound like literal magic to me. How can you possibly abolish an unavoidable tax?
Well, to understand that, we have to go back to 1911.
Okay.
To a Dutch physicist named Heike Kamerlingh Onnes. And funny enough, he wasn't actually looking for superconductors at all.
What was he looking for?
He was just obsessed with extreme cold. He had recently figured out how to liquefy helium, which that allowed him to cool materials down closer to absolute zero than anyone ever had before.
Wait, let's define absolute zero real quick. That being the theoretical point where all thermal energy is just gone, right?
Yes.
The temperature where atoms literally stop vibrating entirely.
Exactly. It's roughly minus 273 degrees Celsius. Literally the coldest temperature physically possible in the universe.
That is just incomprehensibly cold.
It really is. So Osgood was cooling a wire made of solid mercury down to within just a few degrees of absolute zero. He just wanted to see how its electrical resistance would behave.
Okay, and what was the expectation there? That as the mercury cooled and its atoms stopped vibrating so aggressively, the resistance would just smoothly and gradually decline.
Right, because going back to your analogy, the jostling crowd is calming down.
So the electrons should have a much easier time getting through.
That was the logical assumption, yeah. But that isn't what happened. No. At a very specific threshold, about 4 degrees above absolute zero, the electrical resistance of the mercury didn't just decline, it vanished instantly.
Like completely.
It dropped to exactly zero.
Not some microscopic fraction like 0.0001, exactly zero.
Exactly zero. The entire scientific community was stunned. I mean, it actually took decades and the development of the entirely new field of quantum mechanics for physicists to finally explain how the electrons were getting through that lattice without a single collision.
Because it defies all common sense. I mean, even if the atoms are practically frozen in place, they are still physically sitting there in the wire. They are still physical obstacles. So how do the electrons avoid hitting them?
Well, what's fascinating here is that the electrons fundamentally change how they behave.
What do you mean?
In an ordinary copper wire at room temperature, electrons are these independent, chaotic individuals. They constantly repel each other because they all have negative charges.
Right, like magnets pushing away from each other.
Exactly. But when you cool certain materials below their critical temperature, something bizarre happens. The electrons pair up. We call these Cooper pairs.
Yeah, wait. How does being freezing cold suddenly make chaotic electrons agree to march in perfect lockstep? If two negative electrons naturally repel each other, what unseen force is suddenly binding them together?
It's actually the lattice of atoms itself doing the binding.
Really?
Yeah. Picture a heavy bowling ball rolling across a soft mattress.
Okay, I'm picturing it.
As it rolls, it presses down, right?
Yeah.
It creates a depression in the mattress. Now, if another bowling ball is nearby, it will naturally roll into that depression.
Right, it kind of falls into the gravity well. That makes perfect sense visually.
So, in a superconductor, an electron moves through the lattice of positively charged atoms. Because the electron is negative, it pulls the positive atoms slightly inward toward itself as it passes by.
Oh, I see.
This creates a tiny, temporary area of concentrated positive charge, like a microscopic depression in the lattice. A second electron is intensely attracted to that concentrated positive pocket, and it gets pulled in right behind the first one.
So even though they technically hate each other, the way they warp the environment around them forces them into a couple?
Exactly. And by forming these Cooper pairs, they unlock a purely quantum mechanical effect. All the countless millions of Cooper pairs in the material synchronize.
They sync up.
Yeah, they stop acting as individual particles bouncing around, and they merge into a single, unified quantum state.
Going back to our crowd analogy earlier, it's like a chaotic mob of people suddenly grabbing a partner, organizing into a synchronized marching band, and moving through the hallway in perfect lockstep rhythm.
That is a brilliant way to visualize it.
Yes.
Because they are moving as a single coordinated quantum wave, they just glide through the lattice in perfect harmony with the structure of the atoms.
That is amazing.
No individual electron can accidentally veer off and crash into an atom. And, as we know, no crashes mean no lost energy. Resistance drops to zero.
That is just mind-bending. The individual particles couldn't survive the obstacle course on their own, but by pairing up and moving collectively, they literally rewrite the rules of movement.
It really is one of the most elegant demonstrations that when you assemble enough particles under the right conditions, the collective behaves in ways the individual never could.
Wow. Now, zero electrical resistance is a world-changing property all on its own. But superconductors actually have a second major capability, right?
They do, yes.
And it is incredibly visual. Honestly, if you look up videos of it, it looks like a special effect from a science fiction movie.
You're talking about the expulsion of magnetic fields? known as the Meissner effect.
Yes, the Meissner effect. Let me paint a picture of this for you if you haven't seen it. If you take a chunk of superconducting material and you drop it in a bath of liquid helium so it gets freezing cold.
So it hits that zero resistance state.
Right. And then you take a regular, everyday magnet and drop it on top of it. The magnet won't touch the material.
No, it won't.
It just stops in midair. It just hovers there, floating on an invisible cushion. You can even tap it, and it will spin frictionlessly in thin air. It is wild to watch.
It looks exactly like anti-gravity, but the underlying mechanism is pure electromagnetism.
How does it work?
Well, when you bring a magnet near a superconductor, the magnetic field tries to penetrate the material. But the superconductor responds by spontaneously generating these microscopic, frictionless electric currents all along its surface.
And because it has zero resistance, those surface currents can just spin up effortlessly, right? There's nothing holding them back.
Exactly. And any electric current generates a magnetic field. So the surface currents on the superconductor create a magnetic field that perfectly mirrors and opposes the field of the external magnet.
Oh, I see.
It pushes back with the exact same amount of force, causing the magnet to levitate.
But the really crazy part is when the magnet isn't just hovering but gets locked in place. I've seen demonstrations where you can turn the superconductor entirely upside down and the levitating magnet doesn't fall.
No, it stays right there.
It stays suspended underneath it, pinned in three-dimensional space.
That happens because, well, most superconductors aren't entirely perfect, right? They have microscopic impurities in their structure.
Okay.
So instead of repelling 100% of the magnetic field, tiny, thread-like strands of the magnetic field manage to pierce through these imperfections.
Like little needles of magnetism.
Yeah, we call them flux tubes. The superconductor essentially grabs onto these penetrating threads of magnetism and refuses to let them move. It literally locks the magnet at that exact distance and angle.
So what does this all mean for us? I mean, a hovering quantum-locked magnet is an incredible party trick for a physics lab. But how are we actually using this outside the lab?
Well, the most famous application you might have heard of is maglev train's magnetic levitation. By building a track lined with electromagnets and putting superconducting magnets on the train, you can lift an entire passenger train off the rails. It just floats a few inches in the air.
Meaning there are no wheels grinding on steel rails, zero mechanical friction whatsoever.
Which removes almost all the wear and tear that usually plagues traditional rail systems, while allowing the trains to safely glide at, like, hundreds of miles an hour.
That's incredible.
But the applications go far deeper into everyday life. Like, if you have ever undergone an MRI scan at a hospital, you've relied on a superconductor.
Wait, really? Inside the scanner itself?
Yeah, inside the scanner. To see inside the human body with that level of clarity, an MRI needs a massive, incredibly stable magnetic field. Generating a magnetic field that powerful requires a colossal amount of electric current.
Okay.
If you tried to push that much current through ordinary copper wires, the electrical resistance would generate a lethal amount of heat.
Oh, because of all the collisions we talked about.
Exactly. The machine would literally melt itself from the inside out.
So they use a coil of superconducting wire instead.
Precisely. They use liquid helium to keep the coil near absolute zero. Once the current is flowing through that superconducting loop, it just circulates continuously with zero resistance, zero heat, and zero energy loss.
Wow.
And that creates a perfect, unwavering magnetic field to scan the patient.
That immediately changes the perspective, honestly, because this isn't just theoretical physics. This is a working tool saving lives in hospitals every single day.
It really is.
And it scales up to the absolute limits of human engineering, too. The Large Hadron Collider at CERN, the massive particle accelerator spanning the border of France and Switzerland, that runs on this principle, too.
Without superconductors, the Large Hadron Collider literally could not exist. They use thousands of massive superconducting electromagnets to steer beams of protons around a 17-mile ring at nearly the speed of light.
Unbelievable.
They also use them to contain the superheated plasma in experimental nuclear fusion reactors. These are the tools that are driving the next century of innovation.
Which, brings up a very obvious question. If this technology is so miraculous, if it can power MRIs, float trains, and carry endless electrical currents without wasting a single drop of energy to heat, why aren't the power lines outside my house made of superconductors? Why are we still losing massive amounts of energy on our grids?
You've hit on the greatest bottleneck in modern materials science.
What's the catch?
The catch is the cold. For decades after Anna Win's discovery, superconductivity was only found at temperatures near absolute zero.
And building an MRI machine that requires liquid helium is one thing, but keeping hundreds of miles of neighborhood power lines chilled to minus 270 degrees Celsius is, well, impossible.
It's totally impossible. Liquid helium is incredibly expensive, it's difficult to handle, and it's super prone to boiling away. It simply doesn't scale to global infrastructure.
Right.
However, the paradigm shifted drastically in the late 1980s. Scientists discovered this bizarre class of ceramic materials called cuprates that achieve superconductivity at much higher temperatures.
And I think we need to put higher in massive quotation marks here, just for context.
Very true, yeah. These ceramics became superconductors at around minus 195 degrees Celsius.
Which is still freezing.
To a human being, that is still lethally, instantly freezing. But to an engineer, it was a revolution.
Because minus 195 degrees Celsius happens to be the boiling point of liquid nitrogen.
Exactly, which changed the economics of the field overnight. Liquid nitrogen is super cheap to manufacture. It's actually often described as being cheaper than milk.
Really? Cheaper than milk?
Yeah, and it's far easier to handle than liquid helium. Discovering materials that could be cooled by liquid nitrogen was such a colossal leap toward practical applications that the researchers were awarded a Nobel Prize almost immediately.
But even liquid nitrogen requires heavy insulation and constant cooling systems, right? You can't just leave it out.
Right.
Which brings us to the ultimate prize, the holy grail of physics and materials science, a room temperature, ambient pressure superconductor.
A material you could hold in the palm of your hand, sitting in a normal room at normal atmospheric pressure, that carries electricity with absolutely zero resistance.
Right.
No cooling jackets, no liquid nitrogen required.
Here's where it gets really interesting, though. Because if you pay attention to science news, every few years, the internet just explodes with a viral headline.
Oh, yeah.
A lab somewhere claims they've finally done it. They found the room temperature superconductor, and everyone freaks out. And then, like a few months later, the hype quietly vanishes. What is actually going on behind those headlines?
This raises an important question about how scientific progress is actually made versus how it is reported to the public.
Right.
The stakes are so astronomically high that excitement often outpaces rigorous verification. For instance, some of the most famous recent claims involve materials that did technically reach superconductivity near room temperature. But there was a massive asterisk attached to the data.
They were using diamond anvils to crush the material, right?
Yes. They had to squeeze the material between the tips of two diamonds to create pressures approaching what you would find near the center of the Earth.
Wait, why does crushing it help?
Remember how heat causes the atoms in the lattice to vibrate and break apart those delicate Cooper pairs we talked about?
Yeah, the vibration ruins the pairs.
Well, if you apply immense crushing pressure to the material, you force the atoms so tightly together that they physically can't vibrate wildly, even at room temperature. It basically mimics the stabilizing effects of extreme cold.
Ah, I see. But from an engineering standpoint, that's practically useless. I mean, you can't build an electric motor or a cross-country power line if every single inch of the wire has to be encased in a planetary pressure diamond vise.
Exactly. It is entirely impractical. And beyond the high-pressure caveats, there have been claims of true ambient pressure superconductors that simply evaporated under scrutiny.
Right.
Very high-profile papers have been formally retracted recently because when other independent laboratories around the world followed the recipe and tried to recreate the material, they found ordinary resistance.
The original results just couldn't be replicated.
Exactly. They couldn't be replicated.
And when people read about retractions, it's very easy to become cynical, right? To think that science is failing or just full of false promises. But it's crucial to realize that this isn't science failing. This is the scientific method working exactly as designed.
Science is a self-correcting mechanism. When someone makes a monumental claim like discovering the holy grail of physics, the entire global community immediately tries to break that claim.
They test it from every possible angle.
Right. And if the data was flawed or the measurement tools were calibrated poorly, the community finds out very quickly and the claim is rejected. It demands patience.
Which means the next time a viral headline claims a room temperature superconductor has been found, we should probably all practice extreme patience.
Highly recommend it, yeah.
Wait for the independent labs to verify it before we start planning the utopian future.
But the reason laboratories all over the globe continue to throw billions of dollars and thousands of brilliant minds at this problem, despite all the retractions and the heartbreak, is because that utopian future is entirely within reach if we find the right material.
Let's talk about those stakes as we wrap up today.
Mm.
Why does this matter to you listening to this right now? Imagine a world where a cheap, room temperature superconductor is discovered. The entire architecture of the modern world changes overnight.
Oh, absolutely. The global power grid would become completely lossless.
Think about what that means.
You could build a massive solar farm in the deserts of Australia or North Africa and transmit that electricity thousands of miles to densely populated cities in Asia or Europe without losing a single watt to heat along the way.
That alone would change the geopolitical map of energy. And every piece of technology that uses an electric motor, from the fan in your laptop to the engine in an electric car to industrial turbines, they would become drastically smaller, lighter, and vastly more efficient because they wouldn't have to manage heat waste anymore.
And think about the energy storage crisis.
Oh, right.
The hardest part of renewable energy is storing the power for when the wind stops blowing or the sun goes down. With a room temperature superconductor, you could inject massive amounts of electricity into a giant loop of superconducting wire.
And it would just stay there.
It would just circulate there frictionlessly, storing the energy indefinitely with zero degradation until the city needs to tap into it. It's the perfect battery.
It is rare to find a single technology that would so fundamentally upgrade almost every aspect of human civilization at once. Now, we don't know for certain if the laws of chemistry and physics will actually allow a room temperature, normal pressure superconductor to exist.
Right, that's the big unknown.
The universe might simply demand that we pay the tax of extreme cold or extreme pressure to get zero resistance. But I want to leave you with this final thought.
Please.
Think back to that shopping trolley rolling frictionlessly out of the parking lot. The simple, undeniable fact that superconductivity exists at all, that the universe does allow matter, under the right conditions, to carry energy with perfect, frictionless grace, is an incredible source of optimism.
It proves that the barrier isn't impossible. It's just an engineering challenge.
Exactly. The ultimate energy solution to humanity's power grid and climate challenges might just be a matter of finding the right exotic recipe of elements, waiting quietly in a crucible somewhere right now, just waiting for us to discover it.
That is a really profound reminder of how much of the natural world we still have left to explore.
It really is. Well, thank you so much for joining us on this deep dive into the bizarre, friction-free quantum world of superconductors. Keep questioning the everyday world around you, and we will catch you next time.